So this is the handout for interfaces. An example of interface, this is a syntax for the interface definition. In Java, we use interface, the keyword, to declare an interface, and it's used in a very similar manner as the class keyword, right? So typically we have a public class trash can, right? But this time we just say public interface. In this case, it's printable. So the printable interface includes a single method that says print. So something that will be implementing this specific interface can be used to print things. And of course, they will have to provide implementation for this method, because inside the interface definition, it's a pure contract style declaration. Basically, interface is a promise that there will be classes in our system which will provide concrete implementation of the print method, but at this level we use only a semicolon. Of course, if we had only a few classes and instantiated only a few objects of each type, then we don't have to bother with interfaces and would just simply write everything in the form of concrete methods. But when we have this highly dynamic situation like we try to display with this car racing game, where we have a lot of models to draw and everything is dynamically dynamically comes alive, then we may need some extra help from a set of object-oriented features in our programming language, and interfaces are part of those features, very important features. So like here, I try to demonstrate to you that we can store references of type of a specific interface, if model was an interface, and the interfaces can be used dynamically at runtime to access every single interface reference and do things to these objects, and they all will behave differently according to their actual definition. But the trick is that we can have uniform type of storage that refers to all of these objects in memory. So more of this later on as we explore those examples. But interfaces sometimes can be long. Sometimes they could include a dozen of methods, sometimes more, sometimes more than 20 methods. So some interfaces are pretty long. So, but it's desirable, just as with methods, just as with classes, to create interfaces which include only relevant methods and the methods that are people likely to use when access your classes. So essentially the guideline for the types of methods that we want to include in those interfaces is the same as we mentioned earlier when we said, like, how do you design classes? Essentially, we said the best idea is to keep interfaces of our classes, or publicly available methods of our classes, as small as possible. Do not overextend. Observe commonality. If there are common features between different types of classes, perhaps they should be organized into a hierarchy of classes. So an interface can only contain abstract method declarations and static constant variables. All right, so interface implementation example. Implementation means that now that we're trying to use this interface, but before we can use this interface, we need to have a class that supports this specific interface. So for instance, if we have product with description, code, and price, then we can make it a printable object by saying implements, right? So this time a product is now becoming a class which is capable of supporting all methods that can be found in the printable interface. In our case, this is a small demo, so we only have a print method. And naturally, we define for our product, we just say, okay, we'll give you a single print method, and it'll just print information on the console window. But it's as simple as basically doing this, right? And then make sure that you provide the actual definitions for all methods, like print, which were originally declared in the printable interface. Okay, moving on. Notice that we create a new product which creates object in memory, right? Just like one of these objects in memory. But at the same time, what we capture in the program, the object reference that refers to this product is of type printable, right? So once again, let's demonstrate this. What happens here is that we create an object reference, right? We create an object reference, and we also create an object in memory. An object in memory is called printable, right? So I draw this as a like a little 3D box or brick, and the reference here provides us access to this object in memory. In fact, if we lose this reference, the object will be marked for deletion and eventually garbage collected by Java garbage collection thread. But this reference that we capture by our program, if you notice in this example, is not of type product, not the type of the or the name of the class that we create. Rather, we remember a printable interface reference, and therefore, by using this product by default, the only choices that we have when talking to this or using this reference to talk to our object is limited only to methods that belong to this interface. In fact, so far in the sample we only had print. We didn't have many others in there. So the resulting output is the code, the gadget, for which all of those basically correspond to displaying the properties which were initially given to our product when we used product constructor. So supposedly there is a constructor that uses these attributes to construct an object, right? And so print, despite the fact that we're actually talking to the interface, print clearly finds, as we discussed before, what happens is that this print method is defined someplace for, in memory. There's executable code compiled by Java compiler, executable code, which represents the print method that belongs to the product class. However, we have the printable interface. So it finds an object has a hidden member, hidden pointer to a table in memory which contains a list of, a list of addresses for all methods defined for this object. And one of them will be the print method, and this print method will be located in memory and will be executed right here. Okay, so that's the idea. This is how it works. So magically, we say, use interface, but talk to a product, which is a concrete class which implements all methods in the concrete form, right? So this is the bit of a trick which is played in runtime, and this is hidden, and we can just only theorize that, of course, there is some compiled code in memory when our program starts and gets loaded into memory and begins execution. But this is the underneath, under the hood type of implementation that exists there, right? So the next time we can create another object right here, right? Another object which will be another type of product or something that derives from product, and we can then essentially assign a different object a reference to this existing reference and point it this way, and there may be other methods that exist for this particular object, and this object will have its own reference to another table which will point or contain addresses to other methods which can be invoked through the same reference. So depends on if this was a product right here, if this was a product, right? So this could be a gadget, which is another class that derives itself from product. So as a result of us using this reference to talk to this object, this code gets executed. As a result of using the same reference and pointing it to a different object and calling the same method may result in execution of completely different code as a result. So this is the power of using interfaces. It does this, it implements this kind of behavior, and we refer to this as polymorphic behavior, so that we have one reference, but result of the same call, depending on what is the underlying implementation that we're talking to, will result in execution of different code in memory. And that's polymorphic behavior. This is your dynamic polymorphism in action. Okay, so let's move on with perhaps take a look at another slide. Interfaces are similar to abstract classes. We already had a chance to discuss abstract classes. What makes class abstract is the presence of abstract methods. The variables cannot be abstract. All variables are concrete. And the constructors cannot be abstract. All constructors are concrete. Static methods also cannot be abstract. However, methods can be made abstract by making them by using keyword abstract, and so we can define abstract classes which are intended to be used as the parents or classes at the top of the hierarchy of objects, right? So anytime we create an abstract class in its own standalone existence, it really doesn't make sense. However, it begins to make sense when we have classes that will derive from this class and will be used as concrete classes, but the abstract class interface can still be successfully used to talk to the underlying object. Likewise, the interfaces are sort of like an abstract class version, but they can have only static constant variables, right? The variables that are using static keyword and using the final keyword to say that this is a constant immutable value, and then they only can have abstract methods. So this still, we could use abstract classes to express interfaces, and this is the side-by-side comparison between the abstract class definition and the interface definition.